Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to be talking about enthalpy and reaction coordinate diagrams. Let's get started.
Let's start with some definitions. Enthalpy is the energy of a system, and we represent this with the letter H. Now, what we're really interested in is how the enthalpy changes when we have a chemical reaction. So, delta H is the change in enthalpy. We are going to talk about two ways that energy can change in a system. Exothermic, where heat flows out of the system, and endothermic, where heat flows into the system. So here is a table that helps summarize what is going on in the system. So if we have an exothermic process, our value of delta H is a negative value. It means that heat is flowing out of the system. So an example of this is any kind of combustion reaction. So a fire in your fireplace, or lighting a match, or grilling out using propane. Those are all exothermic processes, and you have even felt the heat of those processes coming out. So heat is coming out of the system. Endothermic processes are the opposite. Our value of delta H is positive. Our heat is going to flow into the system. So an example of this are those cold packs that you use, say like if you sprain an ankle and you crush the cold pack and it gets really cold. That is an endothermic process. It is absorbing heat, which is why it feels cold to us. One of the best ways to characterize exothermic and endothermic reactions is with a reaction coordinate diagram. So let's take a look at those. We'll start with an exothermic reaction. So the first thing I want to do is I want to get labels for my axes up here. So my y-axis is energy. As I move up my y-axis, energy increases. Along my x-axis is the process of my reaction. So I'm going to go from reactants to products as I move along the x-axis. Okay, so here is the curve for my exothermic reaction. I will go over all of these labels. So the first thing I want you to take a look at is how I'm starting with reactants and I'm moving to products. Now notice how the energy changes. The reactants started at a higher energy, but then once I got to products, I was at a lower energy. This is the change of delta H. And you can see how delta H is negative. I have gone down in energy. Now let's talk about this hump right here. That is the activation energy. So when you think about those combustion reactions, you need a spark to start that combustion reaction. You strike a match, or you use that match maybe to light the fire in your fireplace. That is the activation energy needed to start that reaction. You can put wood in the fireplace all day long, but without that spark to start the fire, the wood is not going to burn. We measure activation energy from the energy of the reactants to the top of this curve. And this activation energy is different for all reactions. It can either be a large activation energy or a small activation energy. Now let's take a look at an endothermic reaction. Again, let's get labels on my axes. Y-axis again is energy. As we move up the y-axis, we increase in energy. My x-axis is my reaction, moving from reactants to products. Here's what the curve looks like for an endothermic reaction. I am still starting with reactants and moving to products, but notice how my energy changes. My reactants start low in energy and my products end up higher in energy. This is why delta H is positive for endothermic reactions. I am increasing in energy. Notice what happened to our activation energy. It got very large, but it's still measured the same way. It's the energy of the reactants to the energy at the top of this curve. Now, just because EA is generally larger in endothermic reactions does not mean that they don't occur or they're very difficult to occur. This value can change depending on the reaction, but the shape of the curve will still be the same.
I hope you now have a better understanding of the difference between endothermic reactions and exothermic reactions. Thanks so much for watching.